got to start recording. All right. So and after that, we're going to talk about inference, and basically by inference, you get an insight about our data and our model. So this is basically the loop. In fact, this loop is closed. So we usually start with the data. We do some assumption. We do some modeling, fit the parameters, and do some inference, and go back to our data, go back to our knowledge and insight, and may make modifications to our model. So it's basically, this is the loop of the modern day data analysis. So today talks, we are going to talk specifically about learning the parameters of the Bayesian network when all of the variables are observed. So here's an example. So let's say that here's a graphical model that is given, and the joint distribution of the 5 variables can be written as a set of conditionals and marginals. So so today we are going to talk about what are the appropriate ways of modeling, although this is not the only way, but it's a very convenient way of modeling these conditionals and marginals. So the focus would be first talking about marginal distribution that are here represented by blue, and the red, which are basically conditionals that we talk in the form of generalized linear model. So more specifically, today we are going to talk about exponential families to model the marginals, and generalized linear model for conditionals. And then we say that, well, putting everything together, we can learn the parameters of the graphical model with all of the variables are observed. So let's talk about the exponential family first. So what is exponential family and why do we care about it? In fact, exponential family includes many of the familiar distribution that you have worked with so far during your research or undergraduate or your graduate degree or whatever else that you are doing so far. So very obvious examples of that is Gaussian distribution, exponential distribution, and many other convenient distribution that we work with basically. So this is not just because of the convenience. In fact, there are theories that the exponential families are the only family that the sufficient statistics, we talk about the sufficient statistics and what it is exists, and the size of the sufficient statistic does not grow as you collect more data sets. So basically, you can summarize data set into a lower dimensional representation, and that does not grow with the size of the data. This is very important, for example, when you are talking about online set. It's also is the only family that for which the conjugate gradient, conjugate distribution exists. We talk about conjugate gradient, but that's very computationally very appealing and makes life easier. Although we will talk about non-conjugate case, not today, but in the following lectures. Also, it has other interesting properties. The other properties is that if, for example, you say that I have a data. I don't have the data exactly, but I know what for example, mean and the variance of that data would be. So exponential family is one of the family that if you do maximum entropy to fit the parameters is closer to the uniform distribution. Also, I mean, as I mentioned, we'll talk about generalized linear model. Learning exponential family is the key to understand generalized linear model, and also includes many of the known distribution that we have dealt with so far. So what is the definition of the exponential family? So I'm going to use whiteboard quite a bit during the class today. So the mathematical distribution, the mathematical works. Okay, hopefully it works. So the definition of the exponential family is a distribution that have a form like this. So this is the general form of the exponential family. So this is the probability density that is parameterized by theta. So this is the parameters. This is so-called sufficient statistic. And this is basically it has a basically normalizer, or and this is so-called base measure. I explain it more in detail. Okay, so well, for any density, because the density is a function, in fact, that is non-negative, and if you integrate it over the entire domain, sum to one. So what is special about it? Like, I mean, for any density, you can represent it as x of some function, right? So what is special about this? What is special about exponential family is that if you have, so you can basically write the parameterization of that in a specific form. So if you write the function of the density, you can basically subdivide all of the terms that only depends on x and call it so-called base measure, and all of the terms that come in a form of parameterization, basically the only term that has an interaction between parameters and the functions are shown as a linear inner product, and the rest of the parameters are on the other side. So this is the general form of the exponential family. So we are going to see a few examples of how the distribution that you see on a daily basis can come in this form. So, but to get familiar with the names and things that happen quite often during these lectures, theta is the parameterization parameter of your distribution. Tx is sufficient statistical. We'll go over that more detail, and hx is basically all of the variable, all of the terms in your distribution that has nothing to do with x. It has is only dependent on hx. So give you an example. So let's start with exponential family. Exponential distribution. So exponential distribution is an example of the exponential family. So what is the form of exponential distribution? What is it? EXP minus lambda. Yes. E minus lambda x. You need a lambda here too. And so this is for positive, negative, all over the place. What is it? So x should be what? Positive. Yeah, exactly. So x should be positive. Otherwise, you cannot integrate it, right? Okay. So, and 0 otherwise. Okay, so let's write this guy as a form of exponential family. So I can write this as p of x theta, although is here lambda, we're going to convert it as a px of lambda x, right? And then bring that inside. And okay, anything missing here? Anything missing? Huh? If I say that I'm going to write this distribution as this, anything missing? Huh? Indicator function. Yeah, exactly. So I need some sort of indicator function that says that x has to be positive, right? So then this is your h, right? And this is minus a theta. And this is theta, right? So if I want to write it down, hx is going to be the indicator function, and make sure that it's only defined for non-negative. What is my tx? X, exactly. What is my a theta? Yeah, exactly. So log of 1 over lambda, basically. And well, let's see. I guess if I want to say that my theta is minus lambda, then I need some sort of like a minus here. Yeah. Right. Yeah. So I say theta is going to be my, if substitute that in, is going to be minus theta, right? Because theta is minus lambda. Okay, good. So this is very simple one. Very simple one that you can write it as an exponential family. So let's start with another one that we're probably going to use more often in the class. Okay, so let's start with categorical distribution. So another example of that is categorical distribution. So the categorical distribution, let's say that the categorical distribution takes k value. So x take value between k, right? So how can I write x with parameter lambda? So let's say, that mu is a normalized value of k dimension, right? It's a vector of k dimension, they all sum to 1. So the chance of, so mu k is a chance of px equal to k, right? Sum to 1, right? Okay. So now, how can I write it as probability distribution, and then we'll work it out to make it like exponential family. How can I write it? Huh? Yeah, yeah. Okay, good. How can I write? So it's basically like an indicator, right? Like if I'm k, give me that number, right? If I'm not equal to that number, just kill the rest of it. So one way of writing it is to write it as mu k to the power of some indicator function when x equal to k. And then multiply over all of the k's. Right? Maybe I change this guy to maybe I change this to, yeah, actually I'm fine. Yeah. You agree? This is a form? So I'm arguing that this is also exponential family. How can I massage it to make it exponential family? You have to get some exponent out of it. How can I do it? Huh? Somebody that suggestion? Idea? You have to make it look like exponent of something, and then we'll open it up. Yeah, let's start with that. So let's write it as exponent of a log of this guy multiplied by x equal to k, right? Right? I mean, this guy can be, yeah. Yes. And then because it is x, so this is, then I can write this, I can bring that guy inside. Right? I haven't done anything. I just brought that inside. So now, how does this one looks like to you? Yeah, vector product, exactly. So what that vector product should be? Vectors of log mu1 through log mu k, and the other one. Right, this is like a one-hot representation, right? So the inner product of this one-hot representation. Okay, so
You have to say that the number of parameters are k minus 1, otherwise the derivative of the partition function will not.
So let's do that. So let's do exponents of k till k minus 1. So I'm gonna call this like this for shorthand, right? You know, to avoid writing this again and again. And I'm gonna call this log of mu for shorthand. So let's call this log of mu transpose with 1x. Well, let me call this k minus 1 because you want to take the other one out. So so if you know, so if the vector like is k dimensional, you know it sums to 1. If you know that the first top k, you know the other one because 1 minus that, you have the other one. So so we are going to have 1 minus k minus 1. So basically, this is the kth parameter, right? This is the kth one. If the rest of them are 0, this one become 1. And this will become also I can write the last one as okay, right? I just like, because all of them sums to 1, I said I only want the kth one, right? So this term becomes the first top k state, a 100 representation of that. And this is, maybe I have to write it as k minus 1, 2. So this is all of them up to here except the last one. And for the last one, when all of them equal to 0, this becomes 1. The last one is just like 1 over the rest of them. Okay, so if we work this one out, we can write it down as, so this is, in fact, this is log of mu k, right? The last one. Okay, I can write it down as exp of so remember, this is also coming in the form of this one, right? So I can absorb this term into this term. So I'll write it as mu j mu k, right? And this is the extra term. It's going to be 1 minus right? Because I could have write this guy as I just expanded this, right? Just multiply this with this, multiply this with that, and wrote it down. Right? And absorb this term into 1. Now, okay, if you stare at this, what is my tx? What is my theta? And what is my a theta? So let's start with tx. You can write it as inner product, right? Okay, so what is tx? This is inner product, right? This is inner product.
It's the vector of characteristic function.
Is the vector of? It's like a 100 representation, but it's k minus 1 dimensional.
Oh.
Right? So it's like is basically x equal to 1 through x equal to k minus 1. Right? This is my theta x, sufficient statistic. What is my theta? What is my theta? My theta is this, right? It's my theta. So my theta is a log of mu1 to mu k, log of mu2 to mu k, and so on and so forth, all the way to log of mu k minus 1 to mu k. And this is my partition function, right? And my a is what? So it's basically, so this is my theta, this is my a. Now my base measure is going to be, I'm going to accept only discrete values. If it is not discrete value, yes.
That not UK, it doesn't equals to 1 minus the summation. The 1 should be inside.
1 should be inside.
Inside of summation.
1 should be inside this. This.
No. The row up.
This guy.
Yeah.
Why should be inside? I just, okay. Look, in this term, you sum them up, right?
Yeah, but when you take not, it should be 1 minus not and then summation.
Oh, right. Yes. Yeah. That's right. Yeah, you're right. So it's gonna be log of 1 minus mu k. Yes, you're right. Yeah. But that doesn't change the rest of it, right? Yeah. Okay. So, and I guess this has to change to log of 1 minus sum of mu k. Okay. So now we can spend more time and deriving the other distribution, for example, normal distribution. But I'm going to send you right up, and you can also read it yourself and practice it yourself. But hopefully convince you that basically you can write many of the distribution by massaging it to another forms that looks like exponential of parameters or some function of the parameters. So for example, here we have, I'll get back to you. Here we had we can have a function of the parameters transposed with some function of x that we call it sufficient statistic minus some normalizer that is the normalization of theta, or if you have a function of something else, this, multiplied by a function that's only function of x. So this is only function of x. This is a linear. This is basically a linear function of parameters, and perhaps a nonlinear function of x. And this is only function of theta. If you can factorize your distribution with some parameterization, that's basically exponential family. So theta is called natural parameters. If theta is function of something else, for example, the examples that I gave you, theta is a function of mu. So then that's called, so if, for example, theta is a function of another parameter here, eta, that we showed here, is called curved exponential family. And A is basically the partition function. So basically, so this is the general form of the exponential family. Now let me go back to presentation. So the general form of exponential family is as follows. We have this function that is the sufficient statistic, parameters, normalizer, and base function. But there are some cool properties for the exponential family which makes them very appealing. So let's get
Sorry, what was the base measure for the
So it basically says, so x has to be only 1, 2, 4, 5k. So
That was
if,
already in the one hot vector.
that is already in 1 hot vector. You're right. Yeah, so in that case, h1 can be 1. Yeah, h1 can be 1. Okay, so there are some cool properties of the exponential families that makes them very appealing to us. So one of the interesting properties is that if you take a gradient of a, which is your partition function, is going to give us basically the expectation of the sufficient statistic. So give you an example, remember that we had a function that looks like this. So in fact, you can view this as right? So you can view this as a normalizer. Remember the Gibbs distribution? We have a bunch of factors multiplying each other, and then you have normalized to make sure it's distribution. So that means that if I take a integral of this, that should be equal to the other side. So if I take integral of x theta transpose tx, hx dx, it should become what? Yeah, it's, well, this is the normalizer, right? This is the normalizer.
If you want this to add to 1, we want to.
So this become, so yeah, and then what is the
integral of the whole thing to be equals
1, and then what should I write on the right hand side?
That should be like 1 over exponential of a.
Well, you divide it by that, so it should be e to the power of a theta, right?
Yes.
Right? Okay. Now, let's take a gradient with respect to theta. Let's take a gradient with respect to theta. So gradient with respect to theta is going to be tx exp yes, and this is going to be gradient of theta of whatever that is, e to the power of a theta, right? Okay, so let me divide this by a theta. Divided by a theta, I'm going to get exp theta tx e to the power of a theta hx dx. This is gradient. What is this?
Expectation of Tx under the exponential distribution.
Exactly. So it's expectation of this distribution. This is basically your p, the one that you had here, right? You get this. You get this. Right? So it's expectation. Looks like there's expectation. So the cool property is that if you have a form of A and you take expectation with respect to theta, you get the expectation of the sufficient statistic for phi. So I'm not going to work out the other moment, but you can easily show that if you can take a second gradient, it becomes covariance. Now, what are the, so this is what? This is covariance, right? This is the covariance of the sufficient statistic. What are the properties of the covariance? It's a matrix, right? So if Tx is d-dimensional, this is going to be d by d matrix. What are the properties of it? Huh? Positive definite? Right. Okay, so, and then we show it as positive semi-definite. So this function, the second derivative Hessian of this function is positive semi-definite. What does it tell us about that function?
Convex.
That function is convex. So the cool things about that is that A is convex. And you will see that that comes handy when we want to optimize with respect to theta, which means that we can do a lot of cool things with it. So we keep talking about this sufficient statistic. So what do we call it sufficient? So what is this? It just means as a function of tx. Why do we keep calling it sufficient? What is sufficient about it? So so informally speaking, sufficient so it's called sufficient statistic because it has sufficient information about the x. So what do you mean? What do I mean by that? So you can approach this from two points of view. You can approach it from Bayesian point of view. You can also approach it from frequentist point of view. So if you are a frequentist, the definition of the sufficient statistic is that you can view x as a random variable. You can also view theta as a parameter which is coming from another random variable. So if you are Bayesian, if you are a frequentist will tell you that if I know the information, if I have the information about sufficient statistic of x, I can basically draw the distribution without knowing the parameters. If you are a Bayesian, you put a distribution over theta. The Bayesian will tell you that if you want me to extract if you want me to sample from theta, just give me the sufficient statistic. I don't need to know the data itself. Just the sufficient statistic is sufficient for me. So I'm going to work it out for you that like these two ideas are not inconsistent. They are basically saying the same thing. And all of them is about that you can view it as an information bottleneck. You can have all of this information about x compressed into a lower dimensional representation called tx that does not grow with your data. And I'm going to tell you what do I mean by does not grow with your data. And if you know that, the distribution of p x given tx does not depend on x if you are frequentist. And if you are Bayesian, you say that the posterior distribution only depends on a sufficient statistic. You don't need to know the data. So to work it out a little bit, So let's say that we have this factorization, that one side is theta, one side is x, and the middle is a sufficient statistic t. Right. So if I have this factorization, I can write it as p x given t, right? And I can use chain rule This is so far chain rule, right? I haven't used anything yet, right? So if I'm frequentist, I say that this is enough, right? If I'm frequentist. So I can write this as P X T P theta T. So the joint distribution become like this. So what does it mean? It means that theta and x given t are conditionally independent. That's what it says. And you can easily if you have this assumption, you can easily start writing this distribution of pt theta given tx and use the Bayes rule and get the same thing from the frequency point of view. So this.
So for frequencies, theta would be a random variable. So what do you mean by independent?
Huh?
Uh,
So this is the definition of the frequency sufficient statistic. So frequency says that if you give me t, I'm independent of the parameters. I don't care about the parameters. So I can drop the dependency on theta. Make sense? So this is the definition of the sufficient statistic from frequency point of view. So I started with frequencies, and I get these independencies. And I can retrieve Bayesian point of view by just work out this from Bayes rule. So I can write it as P theta t given x, or I can write it as P theta x given t, exactly the same thing, right? This is Bayes rule so far, right? I haven't done anything else, right? So we know from the frequencies point of view that these terms equal to this term, and these two cancels out. You get p theta given t, which is the other way. So these are consistent. So also you can view it from basically just factorization point of view that I told you earlier. That you have the form of the function. You can write it as all of the terms that are joined between t and x, which is your base measure, and t and theta. That's all it is from sufficient to be sufficient statistic. Exponential family had extra assumption that this function that is function of only x, because there is nothing other than x there, right? And this function that is between theta and tx should have a specific form. So you can define the sufficient statistic for any distribution. Exponential family says that the function that is between theta and x should be linear, x linear, and this can be anything. That's it. That's another view of defining exponential family from sufficient point of view. So I promise that it's important because we believe that this sufficient statistic does not grow with the size of data. By the way, before going there, I showed you a lot of so I showed you a few distribution: categorical distribution, exponential, normal distribution, that are all exponential family. Can you give me one distribution which is not exponential family? Because it seems that it's so general, like a massage the parameters and get this. Uniform distribution, right? Uniform distribution is an example of the non-exponential family that's quite useful. Okay, so now I told you that the sufficient statistic, the size of sufficient statistic does not grow with the data. So here an example. Let's say that we have the x that's coming from this exponential family, and we draw IID samples from it. What is the joint distribution? These are IID, right? The joint distribution is multiplication of all of this, right? So the joint distribution of x1 to xn, which are sampled from this distribution, can be written as multiplication of this base measure and this theta that goes out and sum of the sufficient statistic. Now, what is important here is that if tx, for example, was d-dimensional, the sufficient, you see that this is still can be written as exponential family, right? So this is a new term that I call it, let's say, x tilde, which is the sum of all of those exponential family. X tilde still is RD. So doesn't matter how many samples you got from your data, the size of this does not grow. This is not the case about the distribution that are not coming from the exponential family. The size of the exponential family may grow with the size of the samples that you're getting from. And this is one of the beauties of the exponential families, that the size of this Stays the same. It's always d-dimensional no matter how many data you get. Okay, so where it is useful? It is useful when you want to estimate the parameters of the theta from the data. So now let's assume that this is the data that you have, and you want to estimate the theta from the distribution. So the first thing that you would do is basically maximum likelihood estimation. So you have the data, curly D, which is your x1 through xn, and each of those are, I don't know, n-dimensional, d-dimensional, whatever that is. And you want to estimate theta. One of the principles is that give me the theta that maximize the probability of the chance of data given that parameters. And because they are IID, I can write it as right? Well, this is the multiplication, and so there is no difference between maximizing this or maximizing any monotonous function of that. So I'm going to maximize a log of that because that basically opens up the sum. So this is basically argmax of this. Argmax of this guy is the same as argmax of right? The same argmax. It's just easier to optimize. But the cool things about that is that when you take a log of this function, because of the exponential families, it opens up and make a form like this. You get a term that is independent of the theta. So when you are maximizing with respect to theta, you can get rid of it because it doesn't matter. And you have an inner product between the parameters. This is parameter. And a theta that does not grow with the size of your data set. Is that if Tx is d-dimensional, this is still d-dimensional. And a function that this was convex, so minus of that is concave. So you get a function that is basically you're maximizing something that comes in the form of something like this. This is convex. The minus of that is concave, and this is linear. So summation of a linear function with concave function is a concave function. And because it's concave, you get a unique maximum. And that's a nice thing about it. So how can I get that unique maximum? Remember that if you take a derivative, so let's call this L is a loss function. If I take a derivative with respect to eta, I get the linear term, and I get gradient of A. But remember, the gradient of A with respect to eta was the mean, right? So at the optimum, basically what we are saying here is that the mean of the parameters should be equal to empirical mean. And that's all you need to do. So not only we know that it has a unique solution, we know that's actually a very simple solution. You just like take an empirical mean of your sufficient statistic, set the mean of your distribution to that, you're done. You don't need to do any numerical approximation to verify. So, and then this is called moment matching. So the examples of that, so I didn't show you the distribution of the Gaussian because we didn't have enough time. But you have seen the distribution of, for example, for categorical distribution. Remember that the parameters had the form of, so you remember we had forms like this. This was categorical distribution. So the form of the parameters looked like a ratio of the chance of this dice distribution. So this was our parameters. And so our sufficient statistic was basically one hot representation. So to find the optimal parameters of, of this distribution, all I need to do is that I can collect samples from this categorical distribution represented as one hot. So every time you see one, you get a vector that is one and zero everywhere else. You get two, you get 0, 1, 0 everywhere else. And all you need to do is that convert your data to this format, which is the format of TX, average them, and that's your mean distribution. This is basically, you get your parameters back. And then you also, so you know how to go back from, so remember that we had this form that goes from basically the standard form that you are used to it to theta form that might be a little bit weird, but is easier to work with because it's a linear function. And there's a one-to-one mapping between. So you get your theta, you get your mu's, and you go back to your theta. Right? So if I have theta, I can go back to mu and back. Is this part clear?
If the function is invertible.
The function is invertible. But that's a good point. Maybe I'm not going to go through that, but maybe we should think about like why is it invertible. So basically the recipe is as follows. First you identify that your distribution is coming from exponential family. You derive how the Tx should look like, which is your sufficient statistic, and how the parameters should look like. So because you may have a standard parameterization for your distribution that's coming in form of, I don't know, eta or mu, right? So there should be a function between these two, right? Okay, now you know a bunch of facts. For example, you know that you convert your distribution in form of sufficient statistic parameterization and a theta. Now you know that the gradient of a theta respect to theta is the mean of the sufficient statistic. So that is your mean distribution. So now if I get the mean, I can get the theta back by basically so this is very useful when we have form of distribution. So this is for maximum likelihood estimation. So basically this is the case that our theta is viewed as one vector, as a parameter. You're not assuming any distribution over thetas. But if you're Bayesian, you're not usually happy to basically estimate the theta as one single parameter. We sometimes have some assumption about how the range of the parameters should be. So in the Bayesian case, we are not assuming theta as one single parameter, but there's a prior distribution to that. So in the Bayesian case, you are not interested in maximum likelihood estimation, but you are interested in computing the posterior. So what is the form of a posterior? So we are assuming that we have this data, each of these xi, that are coming as an IID from px theta. And because you have some assumption about your theta and how the range of the theta should be, you have some form of the distribution for theta, which can be a function of some other things, like, I don't know, nu, for example. Let's call this nu 0. So you said that this is my prior distribution. This is how the range of theta should be. I don't know. I'm not assuming there is one single theta. There is a range of theta that are acceptable. That's my prior. And I have samples. I have some observation from the theta. What I'm interested is not estimating one point for theta. I'm not interested in just maximum likelihood estimation. I want to see, given this data that I have, what is the probability, what is the density of theta observing this data set that I have? So this is basically the Bayesian point of view to that, and we are going to see how exponential family help us to compute this posterior in a closed form. Because in general, this is not easy. So what should I do if I want? So let's say that I have a form of this distribution. So what should be the recipe of computing this given the data? This is my data. And this is my data. So what should I do? What's the recipe to start? Bayes rule. Okay. So the Bayes rule is going to be data, theta, data, right?
Times prior.
Well, this is together, right?
Ah.
Right. Okay. So, but yes, we can write it as, what is this term? This is the likelihood. What is this term? This is prior. And what is this term, by the way? A normalizer. What is it? Normalizer is correct. But what is the other term for that? What other term people use to call this? It's the marginal likelihood, right? Or evidence. So it's basically, I can write this as P theta integrating theta out. So let's just start with exponential family, see how far we go with this. So so remember that we assume that x is coming from our exponential family. So px condition on theta is coming from, looks like exponential family. So now let's assume that also theta is coming from special kind of theta is also coming from an exponential family, but we are going to assume a specific form for this. Let's say that theta is has the following form. I'm going to talk good theta, right? Okay. So theta is coming from exponential family as well. But one of the nice things about exponential family is that you can prove that there exists a distribution that the t theta looks like this. Looks like a theta itself. And the form of normalizer of the original distribution. And so also B of the parameters have the same form of A. So this is, so you cannot, in general, you cannot assume that such a distribution exists, because if you assume that your distribution, if you assume that your sufficient statistics, because sufficient statistics is a general function of theta. I'm assuming a specific form for sufficient statistic. I'm assuming that the sufficient statistic is theta itself, and the last element of that looks like a partition function. And if you can prove that for exponential families such a distribution exists. So if I assume such a distribution for theta, you see that computation of the posterior can be very simple. So remember that the posterior of theta given the data is proportional to p theta and t, which is basically p likelihood this. Now I can work out. So remember what we showed here. What we showed here. If I have the data, the form of exponential family does not change. So the sufficient statistic does not change. So it looks like the same. So I'm going to use that to my advantage. So this is basically my x1 through xn. So remember, this would look like my posterior looks like sum of I over n xi's and exponential of theta t sum over txi's minus a theta multiplied by, so this is the effect of likelihood, and my prior, which looks like whatever the parameters that I have, my sufficient statistic that comes in the form of this distribution, minus a theta. So the nice thing about that is that, so I assume that because my new sufficient statistic looks like, the sufficient statistic of theta looks like a theta and a, I was able to write it like this. So I can absorb these two terms together. So this is going to be the same term, and it's going to be absorbed together, and I can write it as theta transpose sum over I1 pxi okay. So these are the parameters of my prior. This tau 0 and nu 0 are the parameters of my prior. Minus, and then I'm going to collect all of the a's together. So a theta n plus nu 0. So remember how my prior looks like. This was my prior. This was my prior. If you compare these two, and remember that I mentioned earlier that I'm assuming that I'm not assuming it can be shown that the form of this function is basically as follows. So I'm assuming that there exists a distribution for which the tx, the new sufficient statistic for prior, looks like this form. So the form of that is theta transpose tau 0, which is the parameter of the prior. And I'm assuming that A is also the sufficient statistic of, and the other term is basically, so if I compare these two terms, they look the same, right? There is a theta transport of something, so, and an A. So if I compare these two forms, it means that I might be able to represent my posterior in the same form as I have up there. So let's make it look like the same. So to make it look like that, I have to have a term that looks like this outside. So so they have the same multiplication. So maybe I multiplied by this term and divided by that. So maybe I write it as theta transpose and I have to multiply it by that again to compensate, and Okay, so now this look like the same term. So if their nominator have the same term, I just need to normalize it to get the same family of the distribution. Yes.
Sorry. Up there you said T of theta is like theta and something in the bottom. I'm not sure what is the dimension of that vector, and then.
What is the dimension of what? Okay. All right. So let me go with the dimensions. So the dimension of the tau 0, so
the whole vector of T.
the original
prior,
one,
basically.
the original one can be anything, but I said that there exists a distribution that this distribution, so this tau tilde has a form of theta plus another scalar. So whatever the dimensionality of the theta was, is that plus 1, because you added extra term to that. So if theta is d-dimensional, the sufficient statistic of the theta is d plus 1, because you have theta plus extra number. Right? And I said that this exists. You can prove it exists.
But then you cannot take the dot product of that with theta itself because it has a higher dimension.
It has what?
Normally multiply T of something by theta itself.
Right.
Do a dot
But remember, this is the distribution. This is the distribution of theta, right? Not distribution of. So now the new parameters of this guy. Right? So if I have if you have an exponential family of theta, I should be able to represent it as some theta, some sufficient statistic of theta with some parameter. Let's call it eta minus a eta and h theta. This is exponential family, right?
And eta has a dimension of d plus 1.
Yes, eta has the dimension of d plus. Whatever the dimensionality of these t tilde is, that's a dimensional. Make sense? Okay. Now it seems that the form of this distribution looks like the same of this form of this distribution, except that I have to update the parameters of tau 0 should be this number, and nu 0 should be this number, because they had exactly the same form. So that means that, so basically what it means is this. If I'm willing to make this assumption about the prior that has this specific form, which basically produce a convenience for me, the posterior is going to be the same form, except that you have to update the parameters. All right. Let's get started again. So what we saw was that, so this specific form of the distribution over prior is called conjugate, because it has a specific form of sufficient statistic, and it results in a posterior that stays in the same family. So basically, the take-home message of this is as follows. If you have a specific form of the distribution for likelihood, if you are willing to make assumption about your prior to be a conjugate of that likelihood, your posterior is going to stay in the same family, hence you can compute the parameters in a closed form. What is nice about it is that at the end of the day, the posterior expectation of the parameters, so which is basically can be written as follows: that what is so this basically is a shorthand of theta when theta is coming from the posterior. That's what it means. Has always the following form, that this was what? This is the empirical mean, right? Which was the maximum likelihood estimation. This was our MLE. Plus the effect of prior. This is the parameter of the prior. So you can view the posterior mean as a weighted sum, as actually convex weight between some, because if you sum these two terms, which are the weights, sum to 1, right? Is a weight between maximum likelihood estimation and the effect of prior. And as n goes to infinity, the effect of these terms washes out. Which means that if you have a lot of data, doesn't matter what kind of parameters you put on your prior, the effect washes out. and you get maximum likelihood estimation. So that should give you an insight that if you have a lot of samples, if you have a little bit sample, your prior can be viewed as a regularizer, which says that if I don't have a lot of data, I don't trust the maximum likelihood estimation because it's just not enough. It should be around this value. So at the end, the mean that it gives you is maximum likelihood estimation plus the effect of the prior. So this was the mean of the prior, and this was the mean of the MLE, and they get combined, and the weight of the weight of the maximum likelihood estimation grows as you have more samples. So far you have seen enough about exponential family. Now we are going to extend it to go and use it for generalized linear model. So what do we care about? So generalized linear model, you probably have seen many examples of that, but we are going to generalize it. You have seen it in the form of linear regression, logistic regression, probit, and so on and so forth. The essential part of this is basically understanding the exponential family. And all this kind of model does is that they're modeling the simplest possible graphical model. So, well, the first the simplest case is that a graphical model has only one node, and you have some data you want to fit to. The second easiest one is a simple conditional, that you have x1 and you have x2 and you have numbers observed and you want to model the conditional. So in the previous slides, I showed you this case that you have one node in your graphical model, how you can fit the parameters to that. In this part, I'm going to talk about another simple case that's simple conditional. I have observation about x, observation about y, and I want to fit the parameters of this conditional. I'll show you that at the end of the day, it becomes some sort of regression. And also another good things about generalized linear model is that if you're happy with the maximum likelihood estimation, generalized linear models are great. You can easily compute the maximum likelihood. Most of the time, it's really easy to train the MLE estimation. But if you want to go to a Bayesian, it's not always easy. So it's not that you can find a closed form easily. We'll go over some of those in the following slides. So as I told you, generalized linear model is like the second simplest possible graphical model. That you have two nodes that are connected to each other. You have a bunch of observations from x and y, and you want to fit the conditional. And then the essential part of that is having the exponential family. So to understand that, so let me start with the general definition of the exponential family. So remember, so let's for a second assume that y is a scalar number, it's just one number. So if it is coming from exponential family, it has the form of py theta exp of theta y minus a theta hy. So remember, so now, first of all, ty is just a simple number, and I assume that ty is basically identity. So I made this assumption. And I want to extend this and add a little bit parameters to that. So basically show you different parameterization, different forms of this function, because later on it comes handy. So I'm going to extend this exponential family to generalize it into, instead of having one parameter, have two parameters. So this parameterization comes at the same thing that you saw on the top. So this parameter is called dispersion. You can view it as a covariance. You can view it as a standard deviation. And it's basically just extension. It's like a generalization of the exponential family. It still has the same form, and it has all of the properties, all of the nice behavior. For example, you can still easily prove that the mean of y, which is expectation of y, is a theta, the derivative of the theta with respect to t. So now, let's say that we are given a pair of x and y's. So there is some features that are given to you, covariate, that are given to you, and bunch of scalar numbers. So these can be a multi-dimensional. So xi can be, I don't know, d-dimensional. But yi's are a scalar. And you are given the pair. So these x and y represent this graphical model that I show you. This is the form that I show you. There is x and there is y. But you're given some observation. We are given some pairs of x and y's. And we want to model this conditional. So what we are assuming here is that we want to model, we want to use a linear function of x's to model the mean or some invertible function of the mean. So there is some parameters that I'm going to combine xi's with, and I'm going to connect that to the mean with some function. That this function has to be invertible. If it is identity, I'm just assuming that the linear function, this linear function estimate the mean exactly. But it can be any, as long as you don't have any loss of information, which means that your function should be monotonous, we are good. And you see that this g function can become handy because it can make our life easier. So to give you, so this is basically, we are assuming that, so this g, so I'm assuming basically x transpose i's, or let me, yeah. Okay, so basically I'm assuming, right. So I'm assuming that there is a function of mu that I can estimate it with a linear function. That's what I'm assuming. That's my modeling assumption. So if I'm willing to make this assumption, then so what do I have? I have some parameters that I don't know. Is the parameters of my linear function. I have some features, and they all get combined together and produce, well, they get linearly combined and produce something else, call it eta, which is basically, eta is just W transpose X. It's just a scalar, right? And they're connected to mean through a function. So I'm estimating a function of the eta, so of mu. So it's like a function of mu, which is, this function has to be invertible. So g minus 1 also exists. And so this is basically the mean of my y. So remember, this was expectation of my ty, but because assume that ty is a y, is that, right? Okay. So, and there was some parameterization of the theta. So this was parameterization of the theta. Okay, this was parameterization of the theta. This is parameterization of y. So this is also connected to theta somehow. How is it connected to theta? The mean. So this is the mean of the exponential family. How is it connected to parameters? Remember this? Remember that? Huh? Yes. So exactly. Remember we had a theta, and if I take a gradient of that, become this, right? So if I want to get an arrow between these two, I have to say that, so this is a, oops. This is a prime. Oh, okay, this should be a prime. And this should be a prime minus 1. Right? This is the diagram of the connection. My features, the parameters that are estimating a function of my mean, some function of the mean that this is our degrees of freedom, and we're going to play with this, and our normalization. Now, so let's make a specific assumption about G. So I'm going to make the following assumption. I'm going to assume that G is A prime negative 1, inverse of the A prime. And also I'm using, because of this is basically my so in that case, so let's work it out a little bit. So how can I estimate W's? As usual, our general recipe for estimating W's is maximum likelihood estimation. So we have a pair of x and y's, and I want to represent this of W and maximize with respect to W's. So as usual, I can write it as log. So the random variables that I have is yi given W's. And so remember that if I take a log of this, x goes away, and we have only sigma. And let's assume for now that sigma is known. So sigma goes out. I can write it as sigma square, sum over all of my data. And here I'm assuming that my I have theta I yi and a theta I. So so pay attention to this, that like this is my observation, but I'm also indexing theta with I, because my theta is a function of my data. Every time that I get the samples, I get the sample here, that changes my theta. So this is why it has to be indexed by my observation. So remember, every time we get the pair of xi and yi, this is what I'm assuming probability distribution, and I'm modeling the joint, right? I'm not modeling the distribution of this. I'm only modeling, if this is x and this is y, I'm modeling p y given x. So I don't care about modeling x. So for me, x is just some feature, some number. So this is indexed by I because it's a function of xi's. So now let's call this. This is I don't know what's going on, so all right. So I'm not sure we have time to finish it, but basically at the end, what we get is we get a form of function that looks like this. I can make a gradient of Li with respect to W by doing the chain rule on with respect to Li with respect to thetas, which gives me a linear function, and thetas with respect to etas, and eta with respect to W. So remember, this is a linear function. Just give me xi. And this is just basically linear function of theta. So it's going to give me yi minus a theta gradient. So which, by the way, it was mean. And some function of theta I with respect to eta I. So at the end, my loss function, which is this, my loss function, becomes sum of the term that has a form of like this. xi minus mu I, some function of theta I, eta I, xi. So now, these so this is like gradient with respect to w. These should become familiar to you because if you don't have this term, this looks like a gradient of the simple regression. So what it says is that if you have a general linear small, it looks like a simple regression plus some term that corrects with respect to your assumption. And so here is a list of the distribution and corresponding g's for that. So if you have the normal distribution, that g function become identity. If you have something like binomial distribution, which you use it for classification, the form of that looks like a logit. This is basically what you derive when you were learning the exponential family. So as I mentioned to you, so the form of the derivative of the log likelihood looks like something like this, that we have a set of observation, a mean, and xi's. And if I want to show it in a form of matrix format, so that each of the rows of the x is the observation, and each of the y's are shown in the columns, it looks like as follows. So what is nice about this is that it looks like a derivative of the regression, except that my mu is a little bit convoluted. And this is a function of w. So you can, of course, use so if you have the form of the derivative, you can simply put it into your optimized stochastic gradient descent or anything you want and converge to the optimal solution. So you can improve the speed of the optimization if you use the second order information that basically shows up as a diagonal form, and unfortunately we don't have time to go over that. But at the end of the day, we are going to have the following forms. We have the form of the gradient, and we have the form of the Hessian if you want to incorporate this. So if I substitute the form of Hessian into my function, so it's going to look like S transpose, that S was, remember, was the derivative of the derivative of the mu with respect to eta. And so what I see here is that I'm interested to connect this to the normal regression. So what I can do is that this term is the same between two terms, and if I can take this guy out, I'm going to get the form. So let me multiply this with S of WT, S WT inverse. I'm going to get a form that looks like XX transpose. XX transpose multiplied by this. And this was exactly the same form they use for normal regression. So that means that I can write the optimization as exactly like a regression, except that one correction term in the middle. So if you use an identity function, this becomes 1, and you get the regression back. If you don't have this assumption, and you are using it for different kind of regression or different form of GLM, S has to be adjusted accordingly. So I'm going to skip on the practical issues and summarize it at the end. So if you're given a graphical model that forms like a Bayesian network, all you need to do is that you want to subdivide it into the form that are set of the pairs that are dependent on each other and fit the parameters. So in this case, x4 is dependent on these two. So this would be one regression. x2 is dependent on x1. x3 is dependent on x1. So you're going to have 3 regression and 1 fitting generalized linear model. So to go back to my original problem, if I write the form of if I write the general form of my joint distribution, I'm going to have independent regression, independent GLM for the conditional term, and basically fitting the parameters for unconditional. Sorry, guys. This time, I guess it was a little bit rushed, but I had a lot to cover. Thank you.